Okay, let's dive right into this explainer and begin a kind of detective journey that is going to completely shatter your classical view of the physical world. I mean, if you look around you right now, everything seems solid, right? Fixed, predictable. But when we zoom all the way down to the fundamental building blocks of matter, the rules we rely on every single day, they just completely fall apart. So we're going to explore the astonishing discoveries that essentially forced scientists to rethink reality itself. And it all starts here. Is an electron a particle or a wave? This incredibly simple question introduces this ultimate paradox that completely broke the classical rules of everyday physics. For the longest time, scientists were super comfortable with their neat little categories. Light was a wave. Matter, like an electron, was a particle, just a tiny measurable speck with mass. But early in the 20th century, that rigid boundary really began to blur, and it set off one of the greatest scientific mysteries of all time. So here is our roadmap for this quantum journey today. First, the dual nature of matter. Second, electrons as standing waves. Third, Heisenberg's uncertainty principle. Fourth, Schrödinger's wave equation. And finally, probability and wave functions. Let's get right into it. Part 1, the dual nature of matter. We start our mystery back in 1924 with the French physicist Louis de Broglie. He basically took Albert Einstein's 1905 ideas about light and boldly applied them to solid matter. Einstein had already shown that light had a dual character, right? It acted like a wave, but also like a particle, which we call a photon. So de Broglie asked this revolutionary question. If light can act like matter, couldn't matter act like light? He introduced this concept of matter waves, completely changing the game by suggesting that yes, solid matter acts like a wave. Now, this is only truly significant and measurable for tiny micro objects. Think about it like this. If you throw a baseball, it technically has a wave associated with it. But because the baseball is so massive, the wavelength is so incredibly small that it's completely negligible to us. But for a tiny electron zooming around an atom, this wave character is everything. It literally defines how the particle behaves. So the crucial takeaway here is this mathematical relationship, which is based on Planck's theory, linking a particle's momentum directly to its wave behavior. De Broglie took Einstein's mass-energy relationship and Planck's quantum theory and just mashed them together. He deduced that the wavelength is equal to Planck's constant divided by the particle's momentum. That means the faster or heavier a particle is, the shorter its wavelength. The absolute genius here was taking a particle property, momentum, and explicitly tying it to a wave property, wavelength. He bridged two worlds that physicists honestly thought were totally separate. Part 2, electrons as standing waves. Let's move to our next clue and see how this builds when we actually try to picture an electron moving in a circular path around a nucleus. We really have to stop thinking about electrons as tiny planets orbiting a sun. Instead, we need to think of them as waves extended entirely around that nucleus. This brilliantly illustrates the physics in action. If the orbit's circumference perfectly matches the wavelength, it remains a merging wave, completely in phase. But if it doesn't match, it crosses over itself and cancels out. Notice how this perfectly justifies those earlier atomic theories? For an electron wave to be stable, the total length of its circular orbit has to be an exact whole number multiple of its wavelength. When it matches, it loops back on itself flawlessly. That's a standing wave. But if the circumference is even a fraction off, the wave goes out of phase, crosses itself, and essentially destroys itself through interference. This is exactly why electrons are only allowed to exist in very specific orbits. Part 3, Heisenberg's Uncertainty Principle. But, just as the whole wave concept started to make sense, Werner Heisenberg introduced a massive complication in 1927. What's really interesting here is the stark contrast. Basically, the closer you look at where an electron is, the fuzzier your knowledge of its momentum becomes. In our everyday classical world, you can easily measure exactly where a moving car is and exactly how fast it's going at the same time. But a wave isn't located at a single neat point. It's spread out in space. So for a subatomic particle, Heisenberg realized that determining both its precise location and its exact speed at the exact same moment is just fundamentally impossible. And this frustratingly elegant equation mathematically guarantees that we can never perfectly lock down a subatomic particle's exact state. It forces us to just abandon certainty entirely. Delta x represents the uncertainty in position, and delta p is the uncertainty in momentum. Their product always has to be greater than or equal to a constant. So if you try to shrink your error in measuring the position down to 0, the uncertainty in the momentum is forced to shoot up to infinity. You just cannot know both. It is literally like squeezing a balloon. You pinch it perfectly in one spot, and it just bulges out uncontrollably somewhere else. Total certainty in the quantum realm is a physical impossibility. Part 4. Schrödinger's wave equation. So, this inherent uncertainty meant exact positions had to be tossed out the window, and that paved the way for Erwin Schrödinger's grand probabilistic resolution. Now, please don't let this dense math intimidate you. Simply look at that Laplacian operator, the upside-down triangle squared, and see it as a powerful translation of those physical standing waves into a beautiful 3D mathematical model. Before this, scientists were picturing these flat, two-dimensional circular orbits, like a coin sitting on a table. But space isn't flat. Schrödinger's math factored in kinetic and potential energy to give us the actual tool to calculate the robust three-dimensional reality of atomic systems. Part 5. Probability and wave functions. Okay, so to ground all this abstract math into reality, we need to understand the actual, tangible outcome of Schrödinger's equations. It is absolutely vital to see the distinction here. Solving Schrödinger's equation gives us a wave function, represented by the Greek letter psi. But while that original wave function is just an imaginary mathematical tool, squaring it gives us the actual, real-world probability of locating an electron in space. On its own, psi often contains imaginary numbers. You can't hold it, you can't measure it, but when you multiply it by itself to get psi squared, everything transforms into tangible reality. Psi squared gives us probability density. Because of Heisenberg, we know we can't pinpoint an electron's exact path, but psi squared tells us the exact mathematical likelihood of finding that electron in a specific 3D volume around the nucleus. Ultimately, the whole reason we bothered navigating all of this advanced math was so we could combine the radial distance and the angular coordinates to predict the exact 3D shapes of the orbitals where electrons actually live. The total wave function breaks down into two distinct parts. First is the radial wave function, which depends entirely on the distance from the nucleus. This is why s orbitals are perfect symmetrical spheres. Then you have the angular wave functions, which deal with the angles independent of the distance. When you combine them, these equations pop out those beautiful distinct orbital shapes, the spheres, the dumbbells, those crazy complex clovers that literally make up all the elements in the universe. I want to leave you with this provocative thought today. We started with the simple idea of an electron as a tiny planet, and we ended up discovering that at the deepest possible level, matter behaves like a wave, its exact position is fundamentally unknowable, and its existence is best described not by certainties but by clouds of mathematical probability. The very chair you're sitting on right now, the device you are watching this on, is made of these probabilistic waves. Kind of upends how you view the solid world around you, doesn't it? Thank you so much for joining me on this journey today. Keep asking questions, and I'll catch you in the next explainer.